morning, everyone. Oh wow, many students missing. Okay, so yeah, so let's start attendance. Crystal, Jan, Sion, Angelia, Tober, Wind, Tober. Okay. Wind, Perry, Harrison, Lucian, Logan, Gary, Ray, Eric, Oliver, Curry, Jason, Aaron, Eager, Kratos, Romeo, Yuri, Johnny, Andy, Trey, Leon, Xenon, Jason, Terry, Link, Marvin, Peter, William. Okay, class 7, Pauline, Willow, Cindy, Penny, Theo, Liu Wang, Murphy, Zegler, Carwin, Carl, Tolman Lee, Henry, Zach, Cornell, Lucas, Andy, Bob, Scott, Ken, Anthony, Maxwell, Charles, Phoenix, Harry, June, David. Okay, so let's start where we kind of left. Okay, so yeah, so we done this, but let's rewind what we were doing last time. So here, um, remember we talked about FM, right? So we talked about this. This is my FM, right? FM has narrowband frequency modulation, and then the other is wideband frequency modulation, right? Here we said well, beta is less than 1, so normally we take beta as 0.2 or 0.3. Here for the wideband we say beta is greater than 1, right? So we did narrowband modulation, remember last time? We did that, right? Now we are doing wideband frequency modulation. So this is wideband frequency modulation now, right? Wideband means, well, now, if I have a frequency modulated signal, here is the frequency modulated signal, right? I can write this signal, well, this is cos, right? It's a real. So I can write down like real of, and I'm using Euler's identity, right? Exponential form, complex exponential form. So here is that complex exponential form, right? Again, since this is periodic, so this signal, right? This is periodic. This is periodic. I can express that Fourier series, right? If the signal is periodic, I can represent the Fourier domain as Fourier series, right? If it's not periodic, then that's Fourier transform. So here, since this signal is periodic, so I can express it in Fourier series. So the Fourier series general formula is this, right? What is C? C is the complex coefficient, right? So here, this is the complex coefficient of this that signal. Now here, this very complex exponential, we call this Bessel function. Bessel function, right? Now, well, how to calculate this? How to calculate this integral? The very tedious integral, right? So we use what is called base. We use what is called here. We'll read that. Okay. Bessel scale to find the K and B value. It's called Bessel function table, right? So this is the table. So we'll be talking about a little bit later. So let's start with first this thing. So this is called the Bessel function. Now here is what we are having, right? If I plug in the Bessel function here, well, in this equation, right? In that equation, if I plug in what I'm getting, I got AC n minus infinity to infinity Gn beta cos 2 pi f c plus n fmt, where ff is the frequency of the modulating signal or massive signal. Now the question is, if I want to draw the, in Fourier domain, if I want to draw this, how would I draw this? The spectrum. If I want to draw the spectrum, how would it look like? How would the spectrum be look like if I want to draw it? I want to draw the spectrum of this. How would it look like? You know the spectrum, right? Remember? Well, when we draw the spectrum of narrow band modulation, narrow band, what here, so this, if I remember, we draw the spectrum something like this, right? If this is my FC, right? If this is FC, then this is FC plus FM, and this is FC minus FM, right? This is the spectrum, right? This is the spectrum. Now I want to draw the spectrum of this white band. So how would I draw that white band spectrum? What would be the spectrum of this signal? This signal. Any idea? Look at this equation. How much would be the spectrum? Here. Or let's say, how much would be the bandwidth here? First, I need to know what is the bandwidth of this signal. Here, how much was the bandwidth here for narrow band? Bandwidth was 2FM. How much is the bandwidth here for this white band from this equation? 2 times FM is for n narrow band. What about the bandwidth? Well, infinity is not possible, right? We don't have infinite bandwidth. So then, how can I find the bandwidth of this wideband frequency modulation signal? So we can find what's called the Carson rule. So here, yeah, this is how we can find the bandwidth. This is called the Carson rule. Carson rule, right? Instead of infinity, we use Carson rule to find the bandwidth of this signal with this wideband frequency. And what is that? This is 2 times delta f max plus b. Well, what is delta f? It is the maximum frequency deviation, right? Plus b means fm. And this is for fm. Similarly for pm is 2 times delta f phase, maximum phase, right? Phase deviation. So that's how we can find the bandwidth. Otherwise, it's infinity. Right. So now let's try to figure out. Let's draw that. Yeah. So how would I draw this? How you can draw this, right? So if you put n is equal to 0 here in that equation, n is equal to 0. All right. What you get? Let's say you get AC cos beta. Well, you get this, right? AC cos AC. This. It is AC J0 beta cos omega ct. Well, omega is 2 pi f ct, right? So what is this? This is carrier, right? This is carrier. Now put n is equal to 1. If you put n is equal to 1, what do you get? AC K1 beta cos omega ct plus omega m ct, right? What is that? And then if you put n is equal to minus 1, so I'm putting different values of n, right? So if I'm putting different values of n, what I'm getting AC J, so minus 1 beta cos of omega c plus minus omega m. Okay, now what is this and what is this? This is carrier, right? When n is equal to 0, right? And then if I put n is equal to 1, I got this. If I put n is equal to minus 1, I got this. If I put n is equal to plus 2, here I will be getting 2 times fm, right? 1. It's omega, that means fm. 2 times, so here minus 2 times. If I put n is equal to 3, I will get plus minus 3 fm. Now, what is this? What is this? This is the upper side band, right? And this is the lower side band. Now, if you draw this, simple, right? If you draw this, what you get? You get you will be getting something like this. If I draw, I will be getting something like this. This is my FM, and here is my FC, right? So, upper side band, I have this upper side band, which is FC minus FM, and then I get the lower side band, FC minus FM. And similarly, the second band, I will be getting this one. This is FC plus 2 FM, and similarly this one, FC plus 3 FM, and so on, right? And so on, well, up till go to infinity. Well, we are not interested in that. So this is how it will look like, right? So this is my carrier. This is my first side band. This is my second side band. Third side, I'm putting on all the values. So I'm getting the band, and I'm increasing. I'm going in this way. The magnitudes are going down and down and down. You see that magnitudes, the amplitudes are going down. So this is the amplitude, right? So they are going down and down. So that's how I will have an infinite bandwidth. But that is not possible. So we don't have infinite bandwidth. So what we do, we use what is called the Carson rule. Carson rule to find the bandwidth. Right. So this is Carson rule. Okay. So now let's go back. Now, so we understood that. Now let's talk about the table. So this is amplitude versus beta. Amplitude versus beta, right? So what is happening here? At beta is equal to 0. Beta is equal to 0. I have carrier, right? Maximum value is carrier. Now when
beta is increasing, right? The carrier, right? With beta, carrier, I am getting the first sideband, then I'm getting the second sideband, third sideband. As the carrier is as the beta is increasing, right? So you will see these are oscillation, right? You could say it's a sine, right? So these oscillations are, see here, they are decreasing in magnitude. They are decreasing in magnitude, right? And as beta is increasing, the magnitudes of or amplitudes of these waveforms are decreasing. These are sidebands. These are all sidebands. So a time will be, for a very large beta, these will die down. They'll go to zero at a very large value of beta, right? So I'm increasing beta, and these oscillations or these sidebands, these are decreasing in value, right? Notice here at certain point, here at certain point, for example, here, right? This point, let's say 2.4 maybe, and then here the carrier, right? This is carrier at 0. These are called null, carrier null. See here at carrier, where carrier, well, this is carrier, right? The carrier is 0 at 2.3 maybe, and then this carrier is at 5.5 maybe, and then this is at 8.9. These are called carrier nulls. Carrier null. This is called carrier null. Carrier null. At here, when carrier becomes 0, let's say 2. Well, at this point, well, let's say 2.4 maybe, and then 5.6, 5.4, and then here at, this is carrier, right? This is carrier here, so 8.7 maybe, yeah, 8.7. See, the carrier is 0. These are called carrier nulls, right? What happened here? All the power contained in carrier at these points is transferred to the sideband. All the power to the carrier is transferred to the sideband, right? This is what this means, carrier null. So we have oscillation, we have oscillatory waveform, we have carrier nulls, right? And this oscillation, they are in positive and negative, right? So when I'm increasing beta, a point will reach for the beta value that these will go to zero, almost go to zero, right? And that equation actually tells us how, right? This equation tells us how it will go to zero, right? Now, okay. So here, the spectrum, we just talked about the spectrum. So here is the spectrum, the 98% power bandwidth of the FF signal. In this case, is basically 2 times delta F max plus F band. This is constant. That's how we can find the bandwidth, transmission bandwidth, right? Now, let's talk about this. Let's talk about this. Yeah. So you see 3 things. Number 1 is positive value, 1 is the underlying value, and 1 are the negative value, right? So the positive values are okay. Negative values, these are basically the 180 degree phase difference, right? 180 degree phase difference, and those who are underlined, right? These are the least significant sidebands. Least significant sideband. Now let's read this table. Let's say at n is equal to 2, beta is 5. N is equal to 2, beta is 5. So how much is the value of this JNB? Was 2 here, and here is 5, 0.047, right? 0.047. This is basically ratio of sideband to the carrier. Ratio of sideband to the carrier. This value is ratio of sideband to the carrier, right? So you can find any value for as long as they are in this table, right? So we can go up to n is equal to 16, yeah, n is equal to 16, and beta 10. We can go beta 10. one is for single band, narrow band, right? Narrow band. Because why is narrow band? Because the beta is less than one, very very smaller than one. So it's a 0.1, 0.2, right? Then, okay, where n, well, what is n? N is the order of the sideband, right? N is the order of the sideband. At n is equal to 0. If n is equal to 0, it is n is the number of sidebands, right? If n is equal to 0, we are talking about if n is equal to 0, we are talking about the n is the order of the sideband. Here, n order of the sideband. So if n is equal to 0, what I'm talking about? Carrier, right? Carrier. If n is equal to 0, it is carrier. And if n is equal to 1, I'm talking about the first sideband, right? Yeah, first sideband. And if n is equal to 2, I'm talking about the second sideband. Right? Yes. And then so on, right? And then we just talk about negative one. Negative means 180 degree phase shift, right? Negative means 180 degree phase shift, nothing else. 100 and remember we draw. Okay, I should draw this downward. The reason is this. If I can see here. No, right? Okay. When you are drawing this, there will be a phase shift of 180 degrees. I should draw it here downward. But I'm drawing it because I'm taking up this value. I'm taking positive value, right? I'm taking positive value. That negative sign shows that it is 180 degree phase shift, right? 180 degree phase shift. So this negative value, these are 180 degree phase shift. These are the sidebands with 180 degree phase shift. Now let's read this graph right here on my right side, on your left side, right? We're talking about this graph. Here, FM is constant and amplitude is increasing. That means I'm keeping the frequency of the signal, modulating signal or massive signal empty. I'm keeping it constant, but the amplitude is increasing. So what's happening here? At beta is equal to, here beta is 0.2. So we are talking about a narrow band signal, right? Narrow band frequency signal, which is just like a AM signal. Remember here we define beta here. See here, beta is 0.2, 0.3. That means it is a narrow band signal, right? So here I'm talking about a narrow band signal. Beta is very small, and narrow band signal is equivalent to, well, you could say it is equivalent to AM, conventional AM. The reason is this, right? The reason is this. The bandwidth. Now here, as I increase, excuse me, as I increase beta, what is happening? If I'm increasing beta, so now the power which was here in the carrier, now that power is taken over by the sidebands, right? When I increase beta further, right? If I'm increasing beta further, more power is going towards the sidebands, right? And then if I increase it further, if I increase beta to 50 or 10, more and more power is going towards the sidebands. So you see here, where we started here, how much, and then it is reducing, right? So where is that power going then? If it was here, all the power was here. Now, when I increase beta, I have sidebands coming up, right? So those are taken, sucked by those sidebands. If I increase it further, right? So more sidebands are appearing. that means more power is distributed in the sideband, and if I decrease it, if I increase beta further, now more and more power is going towards the sideband. And notice here FM is constant, frequency is constant of the signal, constant. Now let's talk about this one here. Now here what I'm doing, I am decreasing FM, right? I am decreasing FM and I am increasing, or amplitude is fixed. So remember the relationship between FM and delta? F and FM, beta is equal to what? Remember beta equal to, okay, so let me write down here the relationship. Beta is equal to here. Okay, this beta, the relationship between beta is delta F max divided by FM. That is the relationship. Now, if, see here, if I here I'm saying FM is decreasing. So if FM is decreasing here, if this is decreased, beta is increasing, right? Or if beta is increasing, this is decreasing. So that's so when beta is, see here, when beta, we started beta 1, right? We have this. Now I increase beta to 10, which means what? If I increase beta here 10, this will be decreasing, right? If this is decreasing, that means the distance between here and here, or here and here, becomes smaller, right? Now increase beta further. Let's say we increase it to 50. If we increase it to 50, this is further going down, right? If this is further going down, that means now I'm getting more closer, right? So I'm getting more closer. So you see here and here, much dense here. Now increase it to 50. So if you increase it to 50, further FM is going down. So if further FM is going down, see there, they are now very close to each other. Very, very close to each other, right? So this is what is happening, FM magnitude spectra for different values, right? For different values, I am changing beta. What is happening here, if I'm changing beta, I'm keeping FM constant, right? So what is happening here, power is distributed among the sidebands. And here, the sidebands are coming closer and closer. The reason is because FM is decreasing. Why? Because beta is increasing, FM is decreasing. So if FM is decreasing, they are coming closer and closer to each other. One thing we will talk about here, yeah, these are two properties of the this Bessel function. Two properties of the Bessel function. The first one, it is called the symmetrical property, and the next one, it is called the power conservation property. What are those? So let's see what are those. Right. So first property here, this one, J minus 1. Sorry, J minus n beta, that is equal to minus 1 n, and it is J n beta. Right? This is called symmetrical property. Symmetrical property. Right? Why it is symmetrical? Okay, so let's say n is equal to 2, 4, 6, and so on. Put an even number. Put n is equal to 2. So what will I get? Why it is symmetrical? Right? If I put n is equal to 2, what I'm getting? I am getting here J minus 2 beta. Here what do I get? If I put minus 2, or sorry, plus 2. In this equation, I'm putting n is equal to 2, 4, 6. So J minus 2 is equal to, here if I put 4. J what? J2 beta, right? What is this? What are ends? Ends are the side bands, right? Ends are the side bands. These are ends. We already defined these are the side bands. Number. So this is symmetrical property. See here, if I'm putting even number, I'm getting this, and if I'm putting odd number, I'm getting. So this is symmetrical property. Now, second property is called. Second is called the power conservation property. Power conservation, right? Which is this. J square n beta, where n is minus infinity to infinity. That is equal to 1 for any value of beta. For any beta. It's called power, and you can tell here, this is basically power remains constant here. So what does that mean? Power remains constant. Power remains, from this equation you can tell the power, and basically this is, remember Parseval's theorem? Parseval's theorem, this thing, this one is Parseval's theorem applied to Fn. Parseval's theorem. Remember Parseval's theorem, right? Applied to, Parseval's theorem applied to Fn, frequency modulation. Remember Parseval's theorem, right? So we are applying that to here. So we say, well, the power will remain constant. And this equation tells the power, this is power, right? It will remain constant. Now, if total, if beta is increasing, right? If beta is here, see here, if beta is increasing, before, when beta was 0, all the power was in carrier, right? This is carrier. This is carrier, right? Now, if I increase beta, so the power is being transferred here. So power is given to those side bands, right? So at the end, the power will remain constant. Power first in the carrier, if I have side band, power is transferred to the side band. But at the end result is power will remain constant. And this equation tells that the power will remain constant. It is equal to 1. You sum all the side band power, every power, it should be equal to 1. That means power is constant. And where is that power coming from? It is coming from carrier, right? As you increase beta, the power is transferred to the carrier. But eventually, if you add up, it will have to be equal to 1. That means it is constant. So that's what the wideband frequency modulation is. Now let's move forward. And we talked about this. So now we talked about Carlson's rule, right? So this is Carlson. So one more term is called deviation ratio. Deviation ratio is peak frequency deviation divided by bandwidth of the massive. Frequency deviation maximum divided by bandwidth of the signal is called deviation ratio. Okay. So now your turn. Solve this question. The FM signal is described by the. Oh, do you have today a colonial session today? Today, go there. If you go there, you will get good training in that signal. Yes, I'm telling you, go there. Yes, for sure. If you are busy, very busy, still get some time for this. I have given her practice test, right? And that will help you a lot. Okay, so I can't say more. I can't say more. Okay, so yeah. Okay, in the exam, what I can do, and you will see, if you go there today, you will see this kind of question, which are coming, well, like this question coming in the exam. You will see this kind of question in the exam. And the practice test also. So go there, solve with her those questions also. And also, well, I have chapter 4 as well. Here we are doing chapter 5. So here we are covering, today Like I give you this question. Here I would change it to, let's say, 100. I change it to 50, right? I change this to 10 raised to the power 4. I change it to 10 raised to the power 6. That's what I can do, right? Maximum. Otherwise, what will I do? Same thing I'm finding. So now, question number 1. Here is the signal, FM signal. Okay, one more thing. Probably you are not given this. If you are not given this, you know what is the phase here, right? You know this is the phase, right? FM signal, inside this is the phase. This is the frequency and this is the phase. Remember, we have frequency and phase. So this is the phase. There you go. Now here, how much is the maximum frequency deviation, delta F max? Yes. Okay. A. How much is delta F max? Yes. How do you find delta F max? Yes. How do you find delta F max? By doing what? This is, yeah, by doing what? By doing what? Well, remember instantaneous, okay. Remember what is, okay. Remember what is instantaneous frequency of IT equal to? FC plus 1 over 2 pi d phi by dt, right? Right? Now, take it over there. What you get? Delta F, right? So first you need to derivate this signal, right? Okay. So you need to take the derivative of this signal, right? Take the derivative of that signal, right? If you take the derivative of that signal and you take FC on that side, if you take FC on that side, well, what is Fi minus FC? What is Fi minus FC? It is delta F, right? Delta F. Fi minus FC is what? Delta F, right? So what is the maximum of delta F? So if I derivate that, I will get some sine term, right? If I derivate, I will get sine here, sorry, cos here, cos here. What is the maximum of cos? 1, right? Yes, 1. That's it. So if I do that, so I will be able to, well, I have this, well, this will be coming on that side, this will also be coming on that side. So I will get this, how much I will get? 25 kilohertz plus 25 kilohertz plus 30 kilohertz, right? So here, my delta F max would be 25 plus how much? 25 plus 30? Yes, 30. 30. So it will be 55 kilohertz. It will be 55 kilohertz. How I got that, right? What I did, I derived this, right? So I got cos term. So if I, see here, if I bring it here, I got delta F, right? How can I maximize? I can maximize here. What is maximum of cos? It is 1, right? So I put 1 here, I put 1 here. Well, when I derivate, what will happen? This will come here, this will come here, multiply with those. You get 25, you get 30. That is delta F max. Now, what about phase deviation? How much is the phase deviation maximum? How you can get it? You have phase, right? What is the maximum of this phase? 8, right? Why? Because sine, what is maximum of sine? 1, right? So I have 5 plus 3, so 5 plus 3, it is 8. Done, right? Now, what about deviation ratio? D. Third, so this is A, this is B, and C. What is deviation ratio? D. Well, the formula for deviation ratio is here. That delta F max divided by B, right? So delta F max divided by B. B means FM, right? Delta F max divided by FM, which is the frequency, right? much is frequency? Here, how much is frequency in this signal? FM. We calculated delta F max, it is 55, right? So that is 55. How much is FM? Here? How much is FM in this signal? You can look at this signal. Tell me how much is the FM? Yes. How much is FM? Any idea? Any idea how much? Yes. Any other volunteer want to say frequency? How much? Great. How much is frequency? FM? You know the definition of FM, right? FM means the signal frequency. So if, for example, if I have a signal which composed of 3 components, a signal may have many components, right? So let's say it has a 3 components. So the FM is the maximum frequency component of the signal, right? So here we have 2 components, right? So what is the maximum of these 2 components? That will be my FM. Remember, what is FM? FM is this, right? This is FM. So this is the maximum frequency. So I may have a signal component which is here, here, but I need to find out this frequency. How much is this frequency? So how much is the maximum here? How much is this frequency? Maximum frequency component is which one? Yeah, that's the maximum frequency because it's loud, right? So yeah, how much is the maximum frequency? Oh, that's okay. That's okay. That's okay. Well, yeah. You read? 10, right? Oops. 10 kilo. So this would be 5.5. 10 kilo. This is consider this as FM1. Consider this as FM2. Right? FM2. How would you calculate FM2 and FM1? Right? How would you calculate that? You have this divided by 2 pi. Divide this by 2 pi, you will get 10 kilohertz. Right? Similarly, divide this by 2 pi. How much you get it? So this is lower, this is higher, so you go with the higher frequency. Right? So that's how you get 10 kilohertz. Right? Now, next is bandwidth of the modulated signal. D, bandwidth of the modulated signal, which means we are talking about the FM signal. How much is the bandwidth? So the first question is, I need to calculate, I need to find out, is it a wide band frequency modulated signal or is it a narrow band frequency? Right? If it's a narrow band frequency, that means beta should be less than, very small than 1. If beta is very small than 1, then I can choose, the bandwidth is 2 times FM. Did I miss someone's attendance? Attendance? Yeah, okay. Yes. 5, 6. Wind?
Yeah. 510 Logan.
5, 1.
6510.
Fine. 1 0.
No longer than yes.
Okay. 621.